The broadcast is now starting. All attendees are in listen-only mode.
Thank you for joining us for today's presentation, Keys to Managing Large-Scale System Projects, the Complexity Challenge, featuring Captain Kevin M. Smith. Today's discussion will explore Captain Smith's ongoing research in the area of dynamic system complexity and implementation. Future sessions will address performance optimization concepts, employment challenges, knowledge fusion, and catastrophe prediction. This symposium will explore various dimensions of Captain Smith's work, including his IGI Global video lecture series, Intelligent Systems and the Age of the Superfunction. Captain Smith is editor-in-chief of IGI Global's International Journal of Aviation Systems, Operations and Training, and has edited and authored several other publications in the areas of technology and engineering management. For more information on Captain Smith's IGI Global research, visit our website, www.igiglobal.com, or contact customer service at the information shown on the screen. Today's webinar will be recorded, and all registrants will receive a link to view the online recording. After today's presentation, attendees will have an opportunity to participate in a Q&A discussion with Captain Smith. You can enter questions using the chat box located on the bottom portion of your GoToWebinar control panel. Feel free to enter questions as we go, and we will address them at the conclusion of the symposium. If you have any other questions, or if you're experiencing any technical difficulties today, you can ask me questions through the chat box as well. Thank you for taking the time to join us. Now I would like to introduce our featured speaker. Captain Kevin M. Smith is an aviator, author, speaker, and a recognized expert in the field of critical thinking. Captain Smith's distinguished military career includes holding the positions of Squadron Commander deployed in the USS Constellation, Senior Instructor Pilot, Top Gun Instructor, and recognized expert in air combat operations. Captain Smith has over 4,000 hours of military flight time, mostly in supersonic frontline fighters. During his airline career, Captain Smith attained captain qualifications in all modern Boeing airliners, including the ultra-modern B-777. He was a line check captain in the B-767 fleet. Over the course of a 40-year flying career, Captain Smith accumulated more than 25,000 flight hours. Assigned as the chairman of a government-sponsored Blue Ribbon Task Force, Captain Smith was directly responsible for the top-down redesign of airline pilot training programs for all U.S. airline carriers. This effort represented the first successful attempt to develop targeted training programs designed to improve the critical thinking skills for airline pilots. Captain Smith has received numerous military awards, including the prestigious Meritorious Unit Commendation, recognizing his exceptional performance as Squadron Commander. He holds degrees in electrical engineering and mathematics and is a distinguished graduate of the U.S. Naval Aviation Academy. At this time, I will turn the presentation over to our guest speaker. Thank you, Captain Smith, for joining us today.
And thank you, Anne, and thank you all for joining this discussion on first of a series of I'm working on my screen. first in a series of discussions on large-scale systems. All right, so I've got to get my screen here working. Okay. And can you see my screen? Oh, I got to hit show my screen button.
Yep, there you go.
All right. So I did that. Are we good? People can see your screen. Click. Okay, so people can see my screen now, right?
Okay, great.
All right. Okay. Okay, so I'm scrolling through it now. So I'm on slide number 3. All right, so let me go ahead and start. Again, welcome everyone aboard, and it's an honor to be here today to discuss with you some which I consider to be fairly important issues. This is going to be more of a conversation than a technical tutorial to keep it perhaps a little bit more interesting, and that's kind of the style that I like. The first thing, let me cover quickly the series. Ann and I have planned a series of webinars periodically as we go forward into this year, and this particular session is what we call session 1, and we're going to try to clarify the actual, which essentially means what do we need to know about large-scale systems and why do we need to know it, and this will help us understand how large-scale systems perform. And session number 2 is the theory. We're going to cover some of the important theoretical aspects, particularly in the area of optimizing performance. And here we're going to use some examples from my work on various high-level programs at the national level to get a handle on that. Session number 3 is tools you can use. We're going to be talking about some of the important tools we can use that have been used and basically have been proven to be quite effective in decluttering the problem space and trying to get a handle on what exactly do we need to do to optimize mission performance. And then session 4 is defining what exactly is mission critical. All right, and this is probably one of the most important aspects of my work. When I got involved in upgrading the airline pilot training program, this was really a major effort for us to go back and to consider analytically for the first time ever what constitutes mission critical. And ultimately we want to figure out how we can manage large-scale system projects and design systems that actually work. All right, so Ann covered the bio. I'm not going to cover that anymore. So that's some of the background information, and you can kind of get an idea of where I'm coming from in terms of this series. And also talked about some of the reference material, and so that's up on the screen here. I'm not going to get into that right now. That's been covered. The series orientation is fairly important here, so I want to touch base on that. The orientation is going to be more from an operational perspective, and we're going to add some analytics in there. We're going to be looking at what's mission critical, and also in this series we will cover some of the analytics of uncertainty and some of the algorithms that we have put together. And on this screen, this happens to be one of the airplanes that I flew as a naval aviator. I put it up there because I think it's a nice picture. Okay, so our mission statement for this series, 1, is how do we improve human performance in complex situations? And the second one is how do we optimize performance of large-scale dynamic systems subject to human control. And we're going to be looking at the keys to managing large-scale system projects from this particular perspective. Series objectives. The first one is understanding large-scale entities like large-scale systems and the environment in which they operate. That's fairly important. Some of the in the past, one of the ingredients that has been missing is the operational environment. That proved to be particularly important as we were putting together this new airline pilot training development initiative. We had to understand more completely the operational environment. And then finally, understanding the mechanisms by which performance can be optimized. Now, this is one of the probably most important challenges that I faced as a manager of these design activities. We were trying to design and implement a very large-scale dynamic system, and to do so in such a way as to optimize performance. And this was one of the most probably the greatest challenge that I had as a manager of these projects. Okay. So we're going to start, after this introduction, we're going to start now with session number 1, and here we're going to be trying to clarify the actual, which means that what we need to know about large-scale dynamic systems that are in fact intrinsically complex, and what is critical about this whole area. Let me just cover some definitions very, very briefly. I don't want to spend a lot of time on this, but some of the stuff is not well understood and goes by a number of names. So first off, let me say that large-scale dynamic systems goes by a number of different names. Unfortunately, there's not one single name that's or term that's been more or less approved. I'm not sure who would approve such a thing, but I refer to what we are talking about here as large-scale dynamic systems. Sometimes they're called complex systems. Other times they're called large-scale complex systems, large-scale nonlinear systems, and large-scale interacting networks. For our purposes here, they all mean the same, right? And we'll stick with large-scale dynamic systems. Sometimes we'll call them just large-scale systems for brevity, but what they mean is that these are large-scale entities, and they are important because they can do things that otherwise cannot be done. An aircraft carrier is one example, a naval task force, a military expeditionary force, large transportation systems, economic systems for large industrial economies. And the list goes on. It's almost an endless list. Anything that's large, all right, could be in certain ways could be considered to be a large-scale dynamic system. So a large-scale dynamic system is one where there are lots of moving parts within the system structure, and Furthermore, some of these systems actually move through time and space. One of the large-scale dynamic systems that I was fortunate enough to operate was the Boeing 777. That's another example. And so these examples are almost endless. So basically anything that is big we could consider to be large-scale. Okay, large-scale dynamic systems. We're going to cover some of the definitions here. They are complex. Now, that's pretty important, and we're going to get back to that again in this session and in others. All right, so the complex nature of these entities are very important. In fact, there's a whole body of knowledge that has grown up around what's called complexity theory, spearheaded by the Santa Fe Institute and other places. Pretty important work. And so if anybody wants to take a look at that, by all means. Large-scale dynamic systems are also nonlinear. They are nonlinear entities, and that's pretty important to understand that, and they are also unpredictable. What does that mean? Well, we're going to cover that, and that's a very important aspect of these entities that we need to understand. Some of the theory that has grown up around large-scale dynamic systems with respect to complexity based upon scientific theories and some of the mathematical theories actually proved to be quite accurate, and they were very, very helpful in some of the programs that I was involved with. A perfect example of a very early but a rather remarkable large-scale dynamic system was the B-58 Hustler. That was an Air Force bomber, was introduced in 1960, and it operated for 10 years. In the Air Force, it operated from 1960 to 1970. You can see, if you can take a look at the picture of the cockpit view, which I have there, you can begin to see how incredibly complex this system was. It was very difficult to fly also, and so that was one of the first attempts at a very large-scale dynamic system. This vehicle actually was able to achieve Mach 2, which meant it was quite a remarkable achievement. Large-scale dynamic systems are complex. They exhibit novel behavior. They exhibit, this is a mouthful, I know, and so, but I apologize for it up front. They exhibit non-intrinsic global attributes. What that basically means is, non-intrinsic global attributes, by the way, are also referred to as emergent properties. What that means is that the components of the system do not manifest these attributes that are manifesting themselves at the systems level. So they're not intrinsic at the component level somehow, and some of this stuff is really unknown. Somehow these large-scale systems will manifest properties at the systems level that do not appear at the component level. And that's pretty important, and we're going to revisit that, because as we get further on into this program, we're going to look at that a little bit more in detail to try to get our arms around that. As a result of this non-intrinsic global attribute phenomena, these systems are discontinuous. Large-scale dynamic systems are functionally discontinuous, and that's a particularly important aspect of it. They are robust, indeed, because they can do things that otherwise cannot be done. However, and this seems to be counterintuitive, but this is one of the aspects of it that we have to deal with. They are subject to catastrophe. And we can see this time and time again. They do exhibit autonomous clustering. This is particularly important. We'll get into that later. And they are non-deterministic. In other words, they exhibit uncertainty. They are unpredictable. Okay? So we cannot exactly predict everything that may occur with respect to these systems. Complexity is, of course, a very important aspect that we're going to be covering here. Complexity means that there are large sets of interacting variables, all right? And we can equate that to complexity, right? So large sets of interacting variables. So we have many components that vary, and they interact. So interacting variables equals complexity. Complex systems behave counterintuitively. That is, a plausible tends to be wrong. J.W. Forster was, I think, the first individual to point this out many, many years ago. And then finally, complex systems are in fact nonlinear. And so we have to understand some of the analytics dealing with non-linear systems. Information, of course, is important here, all right? Information is an important aspect of understanding large-scale dynamic systems, and that becomes one of our challenges, is to figure out what we need to know. And that's why we're going through this, this series, to try to get our arms around that one. Okay, so information involves, in effect, data analytics, or what is also referred to as big data. We're going to take data and try to make sense out of it, run it through some kind of an analytical process or analytic algorithms, and try to understand it from a information standpoint. Now, what we're going to do here in this series is that we're not just going to output just more data, or hopefully in this, as we go through data analytics, hopefully it's better data and better information. But that's not the end goal of this series, and it's not the end goal of my the companion video series and the companion textbook. The end goal of all of this stuff that I'm doing is resides in the area of what we call performance aids, right? So we want to be able to make our systems, these large-scale systems, smarter, right? So intelligent systems are the key. We want to make them smarter, and we want them to understand how to aid the performance of the human, not take over the human, but to provide the human with better performance aids so that the human operator and the manager can function more effectively. Now, dynamics is key here, and one of the things that, you know, in my industry in aviation, one of the things we're beginning to understand is that dynamics, or dynamic situation awareness, is particularly important. All right, and what we had done in the past is we kind of slowed things down and stopped them and took a snapshot picture of things, but we didn't understand that it was the dynamic nature of the environment, of the system, and the interactions going on that was really key to understanding how to improve performance. So we have complexity, we have information, and finally we have dynamics. And that was particularly important in the work I did when I was a naval aviator. We worked quite a bit in the area of dynamics. Like I said, the ultimate end game here for my work and also others that are working in this field is to try to figure out what are the performance aids that we need for these large-scale systems. So for example, one of the things that we'll cover in future sessions is a dynamic type of performance aid to help with what we call kinematics, or a kinematic advisor. And so that's one aspect of it. Now, we can approach performance aids two ways. We can just look at it from a literal standpoint, or the left-hand arrow. We can say, okay, you know, we're going to design a specific targeted performance aid for this specific set of circumstances. Right? I would prefer not to do it that way. All right. Now that might be technologically easier, although I'm not sure that it is. I would prefer that we look at it from a performance model standpoint. So look at it in terms of sets of activities that could be dealt with within the context of a particular performance model. Now, the performance model may need to be a bit more detailed and specific for that particular triggered event, but it's all based upon the performance model concept. Now, I'm just going to very briefly touch on this. This is something that we will cover in future sessions, but I wanted to let you know where we're going with this whole thing. Ultimately, we are moving into the realm of what we call the superfunction. Right now, the superfunction essentially does this. It combines multidimensional attributes to optimize systems level performance. So we take a look at, for example, here we took a look at component A and component B and component C. We link them together in some kind of a coherent way, and through various mechanisms and methods with respect to systems architecture, and we can then look at this thing from a systems or a total standpoint, not individually at the component level, but more from a combined functional standpoint into what we call the superfunction. Now, the capstone superfunction is going to be something we'll cover later. We do have a capstone superfunction idea that we're presenting in the upcoming instructional video. I just wanted to touch on that, just to let you know where we're going to go with this thing in future sessions. Okay, so let me briefly cover some of the problems that we have seen out there in the various industries and communities that are struggling with this problem of what we call the problem of complexity. Right? These, whatever we're doing now in terms of these systems and proliferation of information devices, we are running into some problems. And the problems can be defined as the problems of extreme complexity, as pointed out by some observers recently. The first area is in medicine or medical, particularly surgery, as pointed out by Dr. Gawande in his book, The Checklist Manifesto, which I would encourage you all to read it. It's a delightful book. And he points out that the preventable deaths due to surgical errors are much higher than expected, and they were able to reduce that by using devices and mechanisms that were able to help them manage complexity better, particularly in the emergency rooms and the surgery rooms. In the management area in general, SAP, software giant, and others have pointed out that the quagmire of complexity has cost the top 20 companies over $2.3 trillion in the last 10 years. So enormous losses of productivity due to some serious difficulties with complexity. Under technology or technical systems, human-caused design errors have cost the industry over $1.5 trillion over the last 10 years. Human-caused design errors are largely due to the difficulties with dealing with complex systems. In aviation, which is the industry that I'm most familiar with, there has been an alarming number of mission-critical events resulting in serious incidents and accidents that were amazingly unexpected. All right, and so there's something going on in the area of aviation in terms of these complex systems. These what we call these emergent properties are manifesting themselves. We're beginning to see things that we did not expect, which are typical of large-scale dynamic systems. They behave counterintuitively, and we can expect the unexpected. Under science, literal determinism, which is largely based on Newtonian physics, now is being seriously questioned. There's been some serious work being done in the scientific community, which I applaud, to take a look at some of these areas and aspects of uncertainty. Under education, the industrial educational model is now being questioned, and many people are not considering it to be a viable model. In fact, I was recently at a meeting in the Pentagon where they want to explore the idea of the new information age educational model, not knowing exactly what that might be. In military aviation and in the area of air combat, which is one of the areas that I come from, the problem was that technology and maneuvers were poorly understood because this is such a large-scale dynamic system. It was very, very complex, and as a result, it was poorly understood for many, many years. We finally got a handle on it, not completely though, but we finally got a handle on some of the complexity issues. For design teams, designing to optimize for mission success. And this was, you know, when I was involved with the project to redesign airline pilot training, this was one of the things that we were dealing with. All right, so how do we actually optimize mission success? All right, so how do we design things in order to be able to do that? And that was a real challenge, and we had to go back to the drawing boards and start all over again. Came up with some interesting solutions to that, which we'll cover in future sessions. Design management, of course, many of you undoubtedly are involved in the management side of the business, and you're managing design teams. One of the things, I was there too. All right, I was the manager of this redesign effort for airline pilot training at the national level, and one of the things that we had to do, which was a bit unusual, all right, because everybody thought that we knew what the mission statement was, and the mission statement was actually kind of fuzzy and ill-defined. And so we began there. We began at the mission level, right? And so we, to keep it very simple, we had a very simple statement of the mission. Our mission statement, we kept it as simple as possible. It was mission completion and risk management, right? We want to complete the mission successfully, but not at all costs, all right? We're going to manage risk during the course of the operation. And this is true really for every industry, right? It doesn't matter. It could be aviation, it could be automobile manufacturing, it could be anything, right? We're going to complete our mission, but we're going to do it under the idea that we're going to also manage risk in an effective way. And then we get down to the systems, or the system, if you will, that is going to help us do that. And then further down into the components, remembering that the components do not necessarily give you the full picture of what's going on at the systems level. It's pretty important, and we'll cover this again momentarily. Some of the theories that we found useful is determinism was not useful, right? And so that's because large-scale dynamic systems are unpredictable. So we had to come up with new ideas, and they had to be grounded in some new theoretical constructs. One of them was general systems theory, proved to be pretty important, little bit esoteric. I would encourage folks to go there, but realize that some of the stuff is a little bit hard to understand. There are some recent treatments of the subject that are easier. Complexity theory is another area that a lot of work is being done as we speak, particularly by Scott Page and the Santa Fe Institute. Good stuff, all right, and I would encourage folks to go there and take a look at complexity theory. Decision theory, it's useful up to a point. We're going to get into this in future sessions. All right, now conventional decision theory is a bit limited of what it can do for large-scale dynamic systems. There is an aspect of that which is called operational decision theory, which does a better job, and we'll cover that. In fact, that's covered in a fair amount of detail in the textbook that we mentioned up front. Probability theory, of course, is very useful when you're dealing with uncertainty. And finally, information theory. Again, large-scale systems are complex and nonlinear, and they have the added feature, if you will, or the added attribute of exhibiting emergent properties, or what we call non-intrinsic global attributes. Right? Basically, it means the same thing. All right. And in other words, certain things, certain behavioral aspects, attributes reveal themselves only at the systems level. Again, remember that large-scale dynamic systems are functionally discontinuous. You cannot understand them just dealing with the components, or you cannot understand them at the component level only. Right? You have to be able to put them together in some kind of a coherent structure and look at the interactions between variables. They will exhibit novel behavior. They are robust, and in order to be robust, they need to be event responsive, and that's the key, one of the keys to the managing the large-scale system projects, right? Which is, if we're going to build robust systems, we have to understand that one of the keys to that is that they need to be event responsive, and these events could come from any place across the operational spectrum, and so that's one of the keys to success. Again, one of the defining characteristics of large-scale dynamic systems is that they are subject to catastrophe, and this needs to be front and center in any design effort. How can we work in a very specific way to avoid catastrophe, or at least to give us an early warning that catastrophe is imminent? It's one of the areas of research that I have spent an enormous amount of time in, probably starting 30 years ago. So I'm still working on that one. We've got some pretty good ideas, all right. Need some others to join in this process of catastrophe prediction. I think it's probably one of the most important aspects of whatever I'm doing and others as well. Now, we covered this before. I want to go over it again because one of the things that I have proposed to do is we start embracing the idea of non-conventional thinking as we engage ourselves in the management of these, or managing the projects or operating these large-scale dynamic systems. And non-conventional thinking also goes by the term of critical thinking, analytic thinking. There's a couple of terms that are floated around. Critical thinking, I'll stick with that because that's the most common term. So that would be good for all of us to understand what that is, right? And that's not hard. It's a fairly simple set of ideas. In fact, the last count that I made when I was taking a look at that, there are, if you go to Amazon and type in critical thinking, there are at least 65 books that are offered through Amazon alone on critical thinking. Now, in order to understand this very strange phenomena called what we call discontinuity, some non-conventional thinking is needed, all right? And so the components do not necessarily make up the whole, right? So we have a bunch of components here of the system, and in a moment I'm going to cover some of the specific things that we were faced with when we were redesigning airline pilot training. But for our purposes here, the component orientation has limited value. It's not something that we ignore, but realize that it has limited value because we have to actually put these things together in some kind of a global construct, some kind of a coherent whole in order to understand them more completely. So, functional discontinuity is a particularly important thing that we have to deal with, right? And this is because emergent properties, which we also have referred to as non-intrinsic global attributes, they do not emerge from the component level, right? So you may have a whole bunch of components that look all nice, but when you put them together in some kind of a interacting network, they will not produce what you think that they will at the systems level. So a system or a mission orientation is necessary to design robust systems. That's another key. Interacting variables, let me briefly cover what we mean by that because that's particularly important. All right, the rule of thumb here is that 3 or more interacting variables represents complexity. All right, so I was playing with my screen a little bit here. I apologize for that. All right, so we're at 3 interacting variables, and that represents complexity. The onset of complexity occurs, again, with 3 or more interacting variables. And we can look at that in terms of the complexity level, all right? So actually you can, if you're designing something that's particularly complex, or if you're operating something that's particularly complex, it has lots of components, that are or should be interacting with one another, you may want to take a look at the number of components that you have and consider them to be interactive and come up with what I call the coefficient of complexity. Right? And once you do that, you can then characterize the system that you're dealing with or the system you're trying to design as either moderate, high, or extreme levels of complexity. There's a way to do this. You can use the symmetrical matrix idea if you wish, and there's a number of ways to do it. I use the symmetrical matrix, which I then take the square of the number of interacting variables minus that number again, and it gives you the coefficient of complexity. Now we're getting to the end. I did want to cover briefly some of the stuff that we will be covering again. And this is important. I pointed this out before, and this is particularly important in the field of large-scale dynamic systems and dealing with them or designing them and operating them. They are subject to catastrophe, and that's not well understood. I've got theories of my own because I have seen catastrophe happen quite a bit. So I have some theories of my own about the reasons for it. But we really need together to come up with this this whole thing called catastrophe prediction. Right? If we're gonna solve this optimization problem, we have to be able to deal with this very, very effectively. And so catastrophe prediction becomes one of our great challenges. Now, I'm getting close to the end of this session. I did want to cover a few things to sort of like maybe tie this together, hopefully. I've been working on this presentation for a while to try to make it as understandable as possible. So, but in the area of improving our understanding of these large-scale dynamic systems and how they operate and how we can deal with them in an effective way. Let me end this thing by talking about some specifics with respect to airline operations. All right, in this area that I'm particularly familiar with and that I was involved with. All right, and it's not unique. What we dealt with here is actually not unique to the airline industry. It could be extrapolated across lots and lots of industries and organizations and enterprises. In the airline world, we had a whole bunch of components, which I have listed here on the screen, right? And some of them are not well understood. It doesn't matter, all right? I'm not going to get into the details of these components, and this is just a partial list of the components that reside within the cockpit structure, all right, or the crew station, all right? There's lots and lots of components. Now, they were all designed initially to be individual components. They were not designed to interact or to organize themselves in various clusters, right? And that was one of the problems that we were faced with, is that we had a whole bunch of components in these modern cockpits, and they were all operating independently of one another. And because of that, complexity level rose dramatically, and we had to then figure out how we were going to manage complexity, or as Dr. Gwanda talks about in the surgery aspects of medicine, how do we manage situations of extreme complexity. And Extreme complexity happens when things do not go well, when things unexpectedly occur in the operational environment, and the workload goes through the roof, complexity mounts, and often confusion prevails. So we had to deal with that, and as it turns out, I think you'll find this to be quite fascinating. As it turns out, we had all the components in place. All right, this was this time frame was somewhere in the late 1980s through the mid 1990s, primarily, although it continues to this day. But this is where we really began to take a look at this phenomena of the all of the components were in place, and yet the performance was not improving. In fact, the performance industry-wide was showing some degradation in terms of incidents and accident rates. In other measures too. There was not just those two. There's a number of measures that that all industries use, and this industry is no exception. Performance was not improving, and we had to do something to bring this or to deal with this degraded performance problem, and we looked at all the components. The solution wasn't there, and then we began to look at the whole system and the mission in which the system operated, and finally got to the point where we could understand how to improve systems performance in an operational environment. Some of the components that we were dealing with that were not integrated, that were you might say presented to the operator station as a singularity, was the weather radar, the ground proximity warning system, the LNAV, and so forth and so on. There's a whole bunch of them, right? And those were not integrated together. So we had to figure out how to bring all of this stuff together in some kind of a coherent package, and we began our work in that area. Okay, so we are done with this session on the introduction of this series, and I'm going to turn it back over to Ann, who is on the hot mic with me, and she can summarize from her perspective and then capture any comments or questions that may come up. So over to you, Ann.
All right.
If you are up there.
Here I am.
Oh, okay.
Thank you so much. So we had a couple questions come through already.
Okay.
The first question is, what characteristic of these large-scale dynamic systems was the most efficient and user-friendly?
The characteristic that was the most efficient was the aspects of these systems that were able to combine, and this is really important. All right, so we have to combine or communicate across traditional functional boundaries, right? That was key, right? You cannot operate these things just operating singular components, right? You have to be able to go to the next higher level of abstraction, and to be able to deal with these things, be able to deal with these systems at a much higher level of performance, or what we call performance optimization. And so, for example, and let me give you a real live example. Right? So we're dealing with a dynamic system. Right? The dynamic system consists of, among other things, it consists of an energy package, right, where you're using energy, right? In the case of most dynamic systems, in the case of an airplane, is no different. There are three sources of energy. There's kinetic energy, there's potential energy, and then there's chemical energy in the form of fuel converted to propulsion through our propulsion systems. Okay, so we have energy, and then we have the kinematics, right? So in order to optimize performance, we had to bring those two functional components together, right? So we had to bring the kinematics features, which were largely trajectory management and energy management, together. Once we did that, then a whole new world opened up, and we were able to see dramatic improvements in performance. It was really quite remarkable what we were able to observe, and we did a lot of testing, enormous amount of testing, operational testing, and so that was a real breakthrough right there. Okay. Yes. Hopefully I answered that. Over to you, Ann.
All right, next question. What do you predict for the future of large-scale systems?
Good question. The future of large-scale systems is that they are going to become more intelligent. Okay, they're going to become more user-friendly. They're going to become more intelligent. They're going to be true assistants. All right, they are not going to take over the world. I know this is a fantasy of many, right? That the robots will take over the world. I'm not going to go there. I mean, that's for other people to deal with. But what I'm looking at is truly intelligent systems, and the Department of Defense is calling them human-machine synergy, right? The machine is going to become smarter in this way, and this is really key. The machine is going to be able to automatically adapt to changing operational conditions and provide the human with real-time performance aids. Right? That's the wave of the future. That's something that I'm working on, and a lot of other people are working on. All right? This is really exciting stuff. All right? This is really, really exciting. We can, and we can. Right? There is no technological barrier to what I just said. Okay? And that's, I know it sounds crazy, but it's absolutely true. Okay? And I've worked with some of the very top development laboratories in the country, all right, including Boeing Advanced Systems Group, all right. I work with them. All right. There is no technological barrier to what I'm talking about. What we need to do is we need to focus our attention on the algorithms. Once we get that, and there's been some great work done in this area, right? But once we get the algorithms in place, these large-scale dynamic systems can become much more intelligent and be able to automatically adapt themselves to changing operational conditions and be right there with the human operator. All right, assisting the human operator and not being a nuisance, right? Right now, a lot of these systems in complex situations are more of a nuisance than a help. I want to change that dynamic. Okay, and many other people do too, and I think that's the way of the future. I think that is that is an exciting field to get involved with. The more the merrier. All right, there's lots and lots of opportunities there for some great work. Okay, over to you, Ann.
All right, next question. There are currently self-driving cars being built. Do you foresee there ever being self-flying planes?
No, because the not for the foreseeable future, and the reason for this is because, and I go all the way back to my work on the. I was on the original design team for the cockpit for the Air Force F-22, and that was one of the questions we had back then when we were designing the F-22 flight deck, and it's still today. One of the challenges that we all have as designers is that we have to understand the operational environment for what it is, not for what we want it to be. And what it is, it's very, very unpredictable, which means technically is that the operational environment is unpredictable, and it will manifest novel events. All right. Now, a novel event is can be described in decision theory terms as a type 1 decision. I know this is getting a little bit esoteric, but stay with me here. All right. A type 1 decision has no known alternatives, and so problem structuring is required, which basically means that, all right, that we have to identify the alternatives in real time. Now, a perfect example of this, this is as close as I can come to from recent examples, is that the miracle on the Hudson, when Captain Sully was able to ditch that airplane that lost both engines on departure out of LaGuardia. That was a novel event, all right, and he was able to do that because humans can do that, all right, machines can't. He didn't really have the alternatives were very, very poorly defined and stuff like that. So the answer is no, but we can do an awful lot more with performance aiding. Okay, we can relieve the human operator from a lot of administrative detail. We can relieve the human operator from a lot of cognitive overload and stuff like that. So yeah, there's a lot of things we can do to aid the human and capitalize on some of the unique qualities of the human brain. Okay, how did I do with that, Ann?
Great. I think, yeah, I was like really excited to hear your answer there. Kind of along the same lines, the next question is the element of human error inevitable? Is there a way to create a foolproof large-scale system?
Yes, there is, and we're going to get into this in future sessions. And this is probably one of the most exciting aspects of this whole area of inquiry, and that is that large-scale dynamic systems need to be understood utilizing current a current set of situations need to be understood as a future event. Right. Now, what does that mean? It means that we do not operate large-scale dynamic systems from the present. It sounds crazy, doesn't it? Right. Mm-hmm. Well, it's actually not. Right. And what it is that we do what is called outcome prediction. We do outcome prediction. Right. In other words, we take a set of circumstances that are currently happening right now. right, at time 1, T1, and we project that out, right? We project that out sometime, time and place in the future. Now, in these large-scale dynamic systems that travel through the atmosphere, the rule of thumb is you have to be somewhere between 5 and 10 miles in front of the vehicle. What does that mean? You have to be mentally there, right? You have to be, your reality structure is actually someplace in the future, right? Now, if we can extrapolate that to every single industry, it doesn't matter what you're doing. It could be railroad cars, it could be airplanes, it could be surface vessels, it could be submarines, it could be anything that you can possibly think of that moves. That is a huge improvement in performance. If we can take that and make sense of it analytically and display that information, right? In other words, take current situations and display the most likely situation that will occur sometime in the future. I mean, that has got to be one of the most exciting aspects of this whole line of work, and it's something that I have proven in operational studies to work in a way that is it kind of boggles your mind. I mean, I've seen performance improvements that have exceeded 100%. Literally. I mean, I've in some of the case studies I've done, these are real operational studies that I've done with real flight crews, right? I've seen performance improvements that exceeded 100% by getting them in front of, right, the problem, right? Get them out in front of the problem, right? Which basically means future projection, outcome projection, or prediction, or there are lots of words that that mean that. Right, and we'll get into that in future sessions, and we'll get in some of the mathematics are pretty exciting that we get into in terms of how we can do that from an analytical standpoint. Okay, did that make sense, Ann?
No, that was great. It
okay.
kind of comes down to like predicting the future almost. You know, you like try to be a step ahead.
You step ahead, and that is, you see, you don't wait for the event. Okay, or you don't wait for the event to completely unfold, right? You respond to an unfolding situation. Does that make sense? In other words, it hasn't completely manifested itself, but you have an idea. You have a you have more than an idea. You have a strong indication that this event will unfold itself and it might become catastrophic, right? So you don't wait for it to become catastrophic, and that's the key. You see, that was the key. You know, if you read the Columbia accident report, the Space Shuttle Columbia, you know, that was in other studies that were done by a colleague of mine, Captain Newhoner, you realize that is one of the keys that we have got to get in our tool bag. Ability to take this brand new incoming information, right, that hasn't yet revealed itself completely, right, but get out in front of it, right, and be able to take that incomplete set of information and use some analytics of uncertainty to predict the future. And that can be done. Now, that can not only be done by the human, and this is the exciting thing about it, right? That can actually be done at least in part by the machine, by these intelligent systems. That really, I mean, this is one of the most exciting aspects of this whole business, is that the intelligence system can be then truly intelligent and be able to provide the human with some meaningful outcome prediction based upon current events. And it makes then the human performance much more, okay, I'm sorry, I was going to say much more better, but, but I couldn't think of another word. But you know what I mean, right? Okay, over to you.
Next question. Are you describing, quote, prediction or detection of events with little noise interfering with analytics?
Well, in a sense, yes. You have to understand that there will be noise, okay? And you have to develop an analytic process up front, all right? So, in other words, and one of the things that, that I've done in my work, and I continue to do this, is that the first the first preprocessor is signal detection. Okay. Now, once a signal is detected in the operational environment, remember now we're not talking technical here. We're talking operational, right? So don't get hung up on what technical capabilities and limitations are. We're really talking about operational. So signals are detected that could emanate anywhere within the operational environment. Okay. Some of those signals are going to be noise, right? So we have to figure out the signal to noise ratio. We have to figure out some aspects of information theory and utilize that, all right? And there are some good theoretical constructs that we can bring to the table in terms of information theory, first developed by Shannon. But yes, one of the first algorithms that we need is to be able to take these raw detected signals and figure out if they're real or if they're false, right? And in my business, there were a lot of false signals. I mean, a lot. It was probably the false signals to the real signals was probably 25% of the signals that came into the cockpit were real, and 75% were false signals. So you have to be able to do that. Can the machines do that? Help us understand that? Yes, absolutely. Yes, there are ways to do that. Yes, and you can put confidence levels on the detected signal. Now, having said that, and we're going to cover this in future seminars here. Once the signal is detected, we have to then figure out, does it represent a non-trivial occurrence? Okay. If the answer is yes, the signal is a non-trivial occurrence, then it becomes labeled as an event. Okay? So let me go back. An event is a non-trivial occurrence emanating anywhere within the operational environment. Anywhere. Okay? Could be any place. If it's a non-trivial occurrence, it is an event. An event is then seriously considered, right? And an event then has attached to it the confidence level. What is the confidence level that this event is real, right? And those confidence levels can be easily determined by the machine. That's not hard stuff. That's pretty simple mathematical equations. Okay. How did I do with that?
Good, good. So this looks like it might be our last question here. Is it safe to assume that some of the recent airplane crashes are related to the failure of large-scale systems?
Yes. 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 The short answer is yes, and the long answer is for certain. One of the things that that I'd like to point out when I talk to people and give speeches and stuff like that is that when you diagnose the problem concerning airplane crashes, right? The flight crew didn't stop working, right? They didn't just shut down mentally, right? They were working on something, right? But whatever they were working on was not effective, okay? What we have to figure out is look at this thing from a systems perspective, right? Why were they not focused on the right things, or why were they not dealing with what in fact was mission critical? Once we go there, then we begin to get some answers, and the answers come from this whole area which we call event analysis, right? So in other words, as part of our system architecture, we want to have an event analyzer, right? And the event analyzer needs to be part machine and part human, okay? So it's kind of a human-machine hybrid, but there needs to be an event analyzer as part of our systems architecture. The event analyzer helps us keep track of not only all the mission critical events, but what is most mission critical. In other words, in some kind of a hierarchy, some kind of a priority scheme and stuff like that. By and large, the crew was aware of the most mission critical event, but was not aware that it ought to have been the highest priority in terms of a crew response. Okay? Hopefully, did that make sense, Ann? Did
Absolutely.
Yeah, okay. So hopefully I answered that. It was a great question, though, by the way. In fact, all of these have been great questions. I'm delighted to participate in this conversation. Was that the last one?
Yeah, that was the last one.
Okay.
So
right.
I just have some.
Well,
go ahead.
No, I was just going to say I thought all the questions were quite good, and I appreciate them. It got me thinking.
No, absolutely.
Yeah, these are great questions. Yeah. So any final comments from you, Ann?
No, I just want to thank you so much for the wonderful presentation. And yes, thank you everyone for your questions and participating in the discussion today. I just wanted to remind everybody that the webinar is recorded and attendees will all receive a link to access it directly. It will also be available online at our website under online symposiums. You can also view previously recorded and upcoming symposiums there as well. We hope to see you at future presentations. Thank you again so much, Captain Smith, for taking the time to put this webinar together for us.
You're welcome. I enjoyed it very much. It was an honor to be here.
And we'll have follow-ups on our upcoming sessions as well.
Yes, yes. Well, I'm looking forward to the next one. You and I will work on some dates, and we'll get that out as soon as we can firm up some dates for future sessions. Yep. Okay.
All right. That sounds great. Everybody enjoy your day.
Thanks, Ann.
Thanks.
All right. Bye-bye.